The known cloning theorem said that we cannot simply copy the state of one qubit and transfer to another qubit. Therefore, we need to use the quantum teleportation protocol, by which the unknown quantum state of one qubit can be transferred to another distant qubit using a pair of entangled qubits. This video will explain the algorithm of quantum teleportation and the codes in Cirq and Qiskit to demonstrate the quantum teleportation protocol. This diagram shows the setup of the quantum teleportation protocol. Alice has a qubit with an unknown state. So in order for Alice to transfer the state to both qubit, Alice and Bob need to share an entangled qubit, which is implemented by the Hadamard gate followed by the CNOT gate. So in order for Alice to transfer the state of this qubit, she needs to perform a CNOT gate on her 2 qubits, followed by a Hadamard gate on her first qubit. After this, Alice will do a classical measurement on her 2 qubits and inform Bob on her measurement result. Bob will be able to restore the state of Alice's qubit by performing some operation on his qubit. In order to explain the protocol, we will break down the quantum state of the entire system at T1, T2, T3, and T4. T1 is the initial quantum state, T2 is after the entanglement, and T3 is after the CNOT operation, and T4 is after the Hadamard gate operation. So at T2, we have the first qubit tensor product with the entangled qubits between Alice and Bob, and then we can, and this is the unknown qubit with the alpha and the beta, and we can expand out. At T3, we will do a CNOT on the T2. So a CNOT, if the first qubit is 0, we will not flip the second qubit. But if the first qubit is 1, we will flip the second qubit. That's why we have 100 become 110, and 111 become 101. At T4, we will apply a Hadamard operation on the first qubit of Alice. So the Hadamard will convert the first qubit into a superposition state. So a 0 will become 0 plus 1, and the 1 will become 0 minus 1. And then we expand out. We got 8 terms over here, and we will group them into this form. And you can see that now, because of the entanglement, the alpha and beta is embedded into the Bob qubit. So in order for Bob to figure out, to restore the alpha and beta, Alice will need to perform a classical measurement. So the classical measurement result will be either 00, 10, 01, or 11. If it is 00, then Bob will have this state, which is what is the Alice state of a first qubit, and we do not need to do any operation. But if the measurement is 1 0, bot will have a wrong state, so bot will have to perform a Z operation, will flip the bit of 1 from minus to plus. If the measurement result is 0 1, again bot will have the wrong state. It will need to interchange the 1 and 0, and this could be performed by the X operation. And if the measurement is 1 1, then in order for bot to restore back the unknown state of Alice, he will have to perform a X operation to change from 0 to 1, 1 to 0, and then followed by a Z operation to flip the phase of this 1 from negative to positive. So this whole operation can be written in this way. This is the result of the first measurement, and this is the result of the second measurement. Okay, this explains the setup of this quantum teleportation protocol. Let us now show how to do this in Cirq and Qiskit. For the Cirq, we import the libraries. Next, we will define the quantum teleportation circuit. So we have 3 qubits. The first one is the one with the unknown state, and then we have another entangled qubits. One is shared by Alice, the other one is shared by Bob. So we will first append the unknown qubit, followed by the entanglement, the Hadamard gate, followed by the CNOT gate, and then we will have the CNOT gate followed by the Hadamard gate, and then followed by the measurement. Finally, Bob will have to restore back using the CZ gate over here. So let's try with an unknown state with an X operation. And if we do if we check what is the Bob vector, we will get 0 0 minus 1. That's before the entanglement. And now we will carry out the simulator on this circuit and then try to restore back the unknown state on Bob's qubit, and again we get 0 0 minus 1, which is tallied with this. Let's take another example. Let's perform a X on the unknown qubit. So now we have a Bob vector of this. Again, we will go through the whole operation of quantum teleportation protocol, and we can see that Bobs have the same state as the initial state of Alice. We can also do the similarly for the Qiskit. We have 3 qubits. We can perform a rotation on the first qubit to position it to any state that we want. Next, we can create an entanglement using the Hadamard gate and the CNOT gate. And in order for Alice to transfer the state, first it will perform a CNOT gate followed by the Hadamard gate and then do the measurement. Next, bot will have to do a X and Z operation depending on the result of the measurement. So let's try it out and see how it works. And this qubit 2 is the unknown state, and this is the circuit for the quantum teleportation protocol. And after the operation, you can see that bot qubit is the qubit 0. This state from Alice has been transferred to bot. This concludes the video on quantum teleportation protocol. If you'd like to feedback on the video, we welcome your comments below. And if you like this video, please share and subscribe to our channel. Thank you.